So deepfake detection, also known as anti-spoofing or forgery detection, is kind of a niche topic which becomes more and more popular just because generative AI, generative content becomes more and more integrated into the modern world. So we're gonna cover it from the perspective of audio, but we'll also shortly go in what we can do with vision, like with face AI. We saw one example yesterday with Elon Musk, for example, and with another example with Eric, our ex-VP. So let's start. So in terms of this deepfake detection and stuff, we should consider it more like a biometric system. So in terms of biometry, there are different types of how identify a human. Yeah, there are your fingerprints, and when you use your older smartphone, you probably have some sort of touch ID. There is a face ID on modern smartphones. There is your voice, which is also another type of biometry which enables systems to authenticate you. There are some more complicated stuff like IOU, as far as I remember. So it's like how you move, something like this, so like connected to the movement, to acceleration. And in terms of voice biometry, so it's an authentication method based on your voice, on your speech. And we consider two systems there. First one is called automatic speaker verification system, or ASV. So it is a system that compares your voice, the owner, with another real person. So instead of me talking to my phone, it's going to be, for example, Mark, and the system shouldn't allow Mark to get inside my smartphone. The analogy can be that if I use your smartphone with my fingerprint, it shouldn't allow me to open it or with my face. So this type of falsification, which we also refer to as attack, is called imposter attack. Another method that exists is, so apart from having real humans that try to get something they should not, like they try to falsify the identity, there are some synthetic systems or some other forgery methods. Like for Face ID, it can be capturing a photo of, let's say again, Mark's face, and showing this photo against the smartphone, it should not open it. For fingerprint, I can make a silicon copy of your finger and try to mimic it as it being your finger, not a silicon one, So what can we do with voice? First of all, we can synthesize it. We can use something like text-to-speech or voice conversion and make algorithmic voice sound like the owner's voice. This type of attack is called synthesized speech attack. Another one is called recorded speech, and it's more like this, taking a photo, but it's taking a recording of your speech using microphone. So you capture me on Zoom, for example, and then try to pass my voice that you recorded from Zoom back to my phone and unlock it. So because it's recorded, it's not my actual voice. It went again from one. It went already from one microphone, so it's kind of processed, and the system should understand that this is not a real speech. This is already processed speech. A recorded speech may sound like something which is impossible to catch, but we'll see if we'll have time how to handle it. So you cannot use, I forgot to say that this system against synthesized speech and recorded speech is called countermeasure system, or CM. So we cannot use only one system because one is against real humans, another is against some other falsification methods. So ideally, our complete biometric system should be combined. It should be ASV plus CM, which we call spoofing aware speaker verification system, or SASS. Any questions until now? No. Yeah, so if you're gonna read voice biometry papers, you may find interesting terminology there. So there is a term called front end and back end. It's not about making websites or something like this. It's so front end is basically what features you use for your model. It can be a waveform, XN, like a sequence. It can be a spectrogram, this image-like representation, step-through coefficients, which is also some image-like representation, or embedded from some other model like self-supervised model. We'll, I guess, go through it today. And backend is what type of architecture you use. It's either like a deep neural network, or back in the days it was a machine learning method called Gaussian mixture model. And the output of your system is probability of audio being falsified. There are some metrics, but I think we can skip them. It's not very interesting right now. So recorded speech. This one may sound like something impossible to catch, but actually there are different things which make recorded speech sound differently. So imagine this is your system, your smartphone, you're the owner of the smartphone, and you're staying here, you're this blue star, and you say like, hey, smartphone, I am the owner. And there is some distance d from your smartphone. And now it's me, the red guy, who tries to record you on another smartphone or with some high quality microphone from this position. And then I will go to the position where you were and talk to your smartphone again and say, no, it's me, the owner, like, get me your data. So what actually happens? Notice that there is different distance between the speaker and the recorder, speaker and the system, and this all has some impact on the quality of the recorded speech. For example, if I'm talking here, but you recorded me from, let's say, outside of this room, you'll probably record something which sounds like me, but of very poor quality. Yeah. Also, imagine yourself being in a, let's say, cathedral. You try to speak there and you always hear yourself speaking with some more volume, or you can hear some sort of echo that some sound reflects from the walls, and your sentence that you said like goes back into your ears. So your microphone, when you record it as this wrong guy, will also capture this stuff. So basically, what impacts is the quality of your recording, is the distance from the system, it's the room size. So if the room is very small and you say something like this, the voice sounds a bit different from having something large. Yeah, and a similar thing is called T60. It's about reverberation. So if there are some musicians within you, you probably know it. If not, we'll see it here. So imagine you're like in a theater on some music concert, you are sitting here, and there is some guy playing the violin. So actually you never hear him directly, like the sound never goes directly from the violin to your ears. You also hear, apart from this line, which is exactly direct, you also hear a lot of reflections. So the sound goes everywhere. It's omnidirectional. And it goes to the walls, it reflects to another wall, it reflects to another wall, and it comes to your ears again. So in reality, you hear something like this. You hear the direct sound, which is the fastest one. You hear some early reflections, which are not so fast, not so direct sounds, but also quite fast and contain useful information. And so-called late reflections that most likely just some sort of colorful noise that can add some colors to a speech, or can ruin it completely and make it sound like like trash. Yeah. So there is one difference between, so both echo and reverberation are about these reflections that we see here. But there is a huge difference that echo is about reflections that are far away from each other. So when we hear something, our ears actually cannot distinguish sounds that are too close to each other. Yeah. So if we hear two different, let's say, signals within like 10 milliseconds, we will probably consider them as one signal. Yeah, we'll hear only the mixture. And this is what happens in reverberation. The reflections are so close to each other that different reflections, they blend, and we hear the mixtured sounds that is like hello, something like this. While echo, because the distance between these reflections is long enough, you can actually hear two distinguishable sounds. Yeah, so you say hear hello, 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 something like this. So to mimic this sort of a reverberation and to understand what is the level of this reverberation, people measure so-called impulse response. Basically, it's what is the response of your room if you give a very short sound. For example, you take a gun, you fire, it's something like very, very fast sound that is loud but quickly goes down, or it can be again a clap like I did. And you record it with your microphone, and that's basically how your system goes from having one short signal to having this multiple reflections that actually transform short signal to something long. Yeah, so if there are no reflections, you would hear only clap here, this direct sound. It's going to be fast. But because you actually hear some continuation of this clap, you actually call these early reflections and late reflections. And if you want to understand how our speech, for example, would sound in the same room, we can record our speech in something which is non-reverberant, non-echoic, without these reflections, and convolve it using convolution like conv-ID with filters defined by this impulse response that we recorded. So let's say we recorded impulse response in a theater. We recorded this in a lab where there is no echo something. We convolve it, and now our speech sounds like it was recorded in the theater, something like this. So another thing that can change the quality of speech is the actual device that you use for recording and for playing. So if you record on a bad microphone, it's probably gonna sound bad. Yeah, or if you make it clip like this, yeah, it changes a bit the sound. If you have some very bad speakers, they also gonna alternate the sound, etc. How do we convolve it? Remember equation from yesterday, xn multiplied convolved with hn. Yeah, it's sum over xn h something minus n. So just definition of convolution for two sequences. Yeah, and this slide is about the quality of the speaker, but we skip it. So because of these differences that occurred by having like a bad microphone, by having all this reverberation, etc., we can actually understand that this is not a signal that was recorded in front of my smartphone, my system for amplification, that it was recorded somewhere else and now it's played back. So one solution that could be used here is to just pre-train some ResNet on some audio data and then pass it here. And this is going to be a very boring solution, but a working one. A more interesting one is, I won't go into too mass details, I will just show this. So the idea is, let's say that you have your input signal X and you calculated the spectrogram for it. Now you want to regenerate this signal through a vocoder as one type of text-to-speech systems in such a way that all information about speaker is preserved and information about reverberation and all those artifacts is slightly transformed. So it's not identical to what it was before, it's a bit transformed by text-to-speech system. Then the idea is that if you subtract one spectrogram from another, you eliminate speaker information, and you are left only with artifacts left from vocoder, artifacts left from reverberation, and artifacts that were transformed, reverberation artifacts that were transformed by vocoder. So this is your reverberation artifacts after vocoder, and your vocoder artifacts. And because these vocoder artifacts are more or less constant, we use the same vocoder all the time, we can ignore it. And we say that if we train our deep neural network on these differences, we'll be able to distinguish that this is a recorded speech and not a real one. That's like a basic intuition behind it. Any questions? No. Yeah, so skip this. Yeah, let's move on with synthesized speech. Yeah, this text-to-speech systems. So synthesized speech is something we create via text-to-speech, via voice conversion, or via the combination. For example, we created some text, we typed it, then we generated with some voice. It doesn't sound like me, and then you used voice conversion to transform this voice into something which actually sounds like myself. One interesting thing there is that the artifacts, or like the marks that these systems leave in your audio that would actually make them different from the real audio, are not located in all the frequencies we have in our audio. So some systems may leave artifacts in only high frequencies. Some may live in low frequencies. Some may live in two particular subbands, like one in the middle low, one in the high low. And this is actually very easy to check. So what guys did in this paper, I probably cited it, but I'll add it to the README. So when you cut, so they said, let's say we have some minimum frequency f min and some maximum frequency f max, and let's keep only frequencies between f min and f max and cut everything else. So it occurs that if you remove, so and here the blue color is better than the red one. So this equal error rate metric, the smaller the better. So blue is better than red. So it occurs that if you remove these low frequencies and you go like to the right, your quality degrades significantly. If you remove some high frequencies, it degrades even more. So one can say that useful artifacts are located in the small frequencies and somewhere in the high frequencies for this particular falsification algorithm. So this idea leads to the necessity in anti-spoofing for having different models to capture all the possible falsification. So, for example, one text-to-speech can have artifacts in certain subbands, another text-to-speech can have in other subbands, etc. And you cannot have a model that works perfectly for all the subbands. One reason for this is the resolution that we use for spectrogram. Remember, we had this window when we calculated STFT and the hop size. We shifted this window. So depending on how long is going to be your window, you either can capture time changes better or frequency changes better. So here you see that you can easily distinguish between this small line and this small line. So you have better frequency resolution. Here, they are blurred, so you cannot distinguish between frequencies very well. And if you trained one model with this input, another model with this input, they would like have different benefits. Yeah, one can work better for some sort of frequencies, another can work better for other sort of frequencies or for temporal stuff. So a good idea would be to fuse or ensemble different models. We train one with one front end, another with another front end. We take their scores or we take their embeddings and we fuse them. And for fusion, we saw different versions yesterday. It can be either like addition, it can be attention, it can be product, it can be some neural network on top of this, some machine learning algorithm. And we pass these scores or embeddings as a new input features, and this machine learning thing or summation or addition returns our final score. And this combination of models performs better than an individual model. And what we have in terms of models, the easiest and at the same time, like certain years ago, one of the greatest models is called light CNN. It's basically a classical convolutional neural network like conv2D, ReLU, batch norm, conv2D, ReLU, batch norm, conv2D, ReLU, batch norm, MLP. But instead of having ReLU, which is here, where we take a max between 0 and the value, we do another activation called max feature map. So how it works? Let's say you have 2n channels in your feature map. You say, let's split them into two parts, first n channels and second n channels. Now I will compare elements in the index I with index n plus y and choose the one which is greater with this max operation. So here you will combine xi with xn plus y. And instead of having 2n channels, the output of your max feature map activation will be something with n channels, with twice as less. Or you could do MFM3.2, where instead of having just max, you also calculate median, and you have 3n channels instead of 2n channels. And for the input features, it can be absolutely anything, like your spectrogram, your MEL spectrogram, your substrate coefficients, anything, and it works great. Why this model is also cool? Because it was inspired by biology, and we covered it maybe 3 or 4 times during the bootcamp, that there is this like MLP, yeah, fully connected neural network that is basically inspired by neurons. We saw with LLMs these experts with Butter, and here this max feature map is called, as far as I remember, lateral activation in biology. So there are some neurons, and when they like communicate with each other, they like give access to some neighbors and do not give access to some other neighbors based on some principle, which is reflected in this max feature map thing. So if you are interested, you can go to this light CNN paper and check how they explain it. Yeah, so it's not lateral activation, lateral acceleration, no, lateral stop, so something is lateral. Yeah, so another cool model is called RONET2, and it works with raw audio instead of having any spectrogram with it. So what's the difference here? We use so-called sync layer, which we covered yesterday, and we'll understand why. Then some rest blocks, some fancy things that we will skip today because we don't have time, and the recurrent neural network. So remember, we talked about this yesterday, that for some modalities, we can take inspiration of how the domain works to actually improve our model. Yeah, we discussed that the traditional convolution works actually as some sort of filtering, where it applies this filter on your input system and either attenuates or magnifies some of your frequencies. And we say that if this first layer looks like this and it tries to actually capture some subbands, let's say directly to the model that it should work like this with these certain subbands. But now, in terms of anti-spoofing, this makes even more sense, because we discussed that artifacts are located in special subbands rather than in the full band. So if we train our neural network to, for example, focus on this certain subband, or in this certain subband, or in this certain subband, and if it can choose which f-min and the f-max to work with, it can actually identify itself what is going to be the best choice of filtering, and it can locate artifacts for many different systems. And you do not, with systems that use something like sync layer, it's a high chance that you do not need this ensembling, this fusion, to make a system robust to different classification methods. And actually, it was also shown that this sync layer allows to better capture information about the speaker. For example, if you train your convolutional neural network and you sum up all these filters you had, and you train a sync layer and sum up all these bands you had, you'll get something like this. And they look kind of similar, but for normal convolution, there is no specific pattern. For sync convolution, you actually can match the peaks with something meaningful. For example, this pitch is the frequency. So we have a peak with a frequency corresponding to, as far as I remember, either male or female pitch. So women speak a bit higher than men usually. So, but if you take an average and calculate what is the basic frequency of the voice, yeah, the peak will gonna be somewhere here. And there is here so-called first and second format, as we discussed yesterday. Some letters like A, like O, they are defined by some peaks in the frequency band, some patterns that are unique for different letters. So actually, this first format is also, as far as I remember, the average of different vowels. So it's SyncNet captures very well the information about how people's voice is structured. Any questions? Yeah.
In this case, the CNN is one-dimensional convolution.
Yes. No, not the CNN, one layer. Sorry. So it's one convolutional layer that looks like this. So before it was HN, where you trained HN with L filters, yeah, and now you have GN. You do XN convolve with GN instead of HN, and to ensure that your response, that your equalization looks like this and not like this noisy stuff, you define your GN as a function of two parameters, f-min and f-max, with this sync and rectangle thing that we discussed yesterday.
Also for the light CNN?
Yeah.
It's still one-dimensional because...
No, this one works with spectrogram-like front ends, so it works with matrices. It's a const2d thing. Yeah. So we'll skip this, and we have 20 minutes. Let's skip graph neural networks for now and move to self-supervised models just to understand why they're cool. Any questions until now? No? Good. People on Zoom? Good. Yeah, so self-supervised models, why do we care? And why it's maybe second most important thing you need to remember from the bootcamp. So self-supervised models are something that allows you to achieve high quality in tons of different tasks with ease. So why? So recall that we talked about such thing called fine-tuning. Yes, that we trained some model on a large data set with, let's say, different classes like dogs, cats. And then we copy pasted our weights and trained with small learning rate on something with small data set where we couldn't collect a lot of data, something like diseases of plants. Yeah, we want to say whether this plant is normal or it's diseased. So the idea was basically, if we train our model on something where there is a lot of data, we can use this knowledge to perform better on data sets with small amount of data. Why? Because if this we have a small amount of data, it's most likely we are not able to capture all the patterns, and we also cannot perform well on test sets because the distribution test set may be noticeably different from the train set. And this is just because small amount of data cannot show all this variety of possible inputs. Yeah, basically, if you train your model only on dogs, yeah, it doesn't work on cats because you have never seen cats. Yeah, even though cats and dogs share some common features. But if you train if you have a huge amount of data with dogs and only small amount of data with cats, because cats are somehow similar to dogs, your model will benefit from having this prior knowledge. Yeah, the problem with huge amount of data is that for many tasks, it's very hard to get paired data, meaning having output for your input. Yeah, like a class label or something like this. So actually, we didn't care about having a class label or some output when we talked about going from huge amount of data and using this knowledge to small data sets. What we actually cared about was seeing a variety of inputs. So the distribution of the test set doesn't look so different from the distribution of the train set. That we have learned about many possible options, and we are robust to out-of-domain stuff. So test sets are now more likely to be more similar to the trained data. So instead of focusing on a task, we actually want to train a model to generate, to represent our data extremely well. So before, we had pairs of X and Y, like input and output, and we wanted our deep neural network to approximate Y. Now we just have X and only X, and we have DNN X, which represents X well. By represents X well, I mean that if there is some feature or characteristic of X, we can easily train some small deep neural network or some small thing to approximate that by, so let's call this like small deep neural network J. Yeah, we can easily train this J to work like an approximate if we pass DNN X as input. In other words, later, we can approximate any class label Y easily by using DNN X as input, instead of directly approximating, yeah, where Y is approximated by DNN X, we say Y is approximated by J DNN X. And if we do only this, we are in the case where we have small amount of data and we cannot generalize well. In this case, because DNN X itself saw a huge amount of data, this JDNN X benefits from having knowledge about this huge amount of data, and it works better. So a simple example could be you have a data set with only clean speech, let's say, and if you pass some noisy speech with a lot of noise, it won't work well. But if you pre-train your neural network on something which is both clean, so there are some clean examples, there are some noisy examples, and then you fine-tune it only on clean examples, there is a higher chance that it's going to be still working with something noisy. Because maybe for your model, representations of noise speech and of clean speech are more or less similar. Yeah? Questions here? No? Yeah?
Maybe it that it inherently tries to learn beforehand how speech is represented, but it means to have like people talking in a sound rather than just random things mathematically, and then we can specify once it has kind of understood how to understand. Like I'm thinking about the scope of images, like the fact that you pre-train on a huge amount of data.
Yeah.
You learn maybe kind of how to read images, and then you can.
Yeah. So this basically tells you how to read, as you said, like input in a certain way that will be easier for us to process later. For example, it might be hard to determine the age of a person by his or her photo. But it might be much easier if we train a model to represent our photos in a such way that by having a simple fully connected layer, we can easily extract the age of this person from this photo. Or maybe it's not just about age, we take the same representation and it can also represent like some other features of this speaker.
Can you say it like that? It sounds a bit like the first neural network is creating an embedding of.
Yeah. It's like a feature extractor, like an embedding representation. Yes, correct.
Looks like a backbone or some kind of tools for image detection of figures. So you have big backbones pre-trained, and then you feed them.
Yeah. So it's common to have like huge models trained on huge amount of data, like ImageNet, like huge VAT, and then utilize its knowledge for something else. The problem is that not all domains has something like ImageNet, where there are a lot of labeled data. For audio, it might be the case you only have a lot of information about like audio, like a sequence, but you do not have any sort of label to use it. Or you want something more generic. Maybe if you train your model on ImageNet, it's good in terms of classification. But if you want to do something which is not about classification, but about something else, maybe doing the way how we handle it here would be a bit better, because it may work for other downstream tasks that are less similar to classification. Clear? What do you mean by the X represent X well? I'm not sure to understand the difference between the before and the now. Before we had desired output, we could we trained on pairs, let's say, again, person and his or her age. Now we do not care about having this age label. We just want to get some representation of this photo from which we can easily later extract information about age or some other characteristic. Clear now? Because we may have a lot of data where we just have a photo, but only like 10 examples where we know the age of a person. Yeah, hopefully it's clear now. So what is the goal of the deep neural? The goal of deep neural network is to create some representation of our input that is first of all compressed, and secondly can represent our data very well. And where represents means useful characteristic about this input can be extracted from it easily. Like for audio example, we say that we can calculate this spectrogram thing and we can see frequencies now which are useful. Now, instead of having this spectrogram, we say, let's use our new model, run it on our audio, and we get a new matrix. And let's use these metrics as our features instead of spectrogram. And it won't be so interpretable in the sense that there won't be a clear idea what's frequency, for example, what the rows of this matrix are representing. But for the deep neural network itself, these features might be even better than having some frequency information. Yeah.
So when you train the first big network, I guess you have to have like carefully choose like several good characteristics to
No.
train it on.
No. So how it works? So okay, so our DNA represents X in a compressed form, and then from this compressed form we can easily deduce the characteristic we want. Yes, correct in the chat. So how does it work? So there are actually different ways how to train such models, and the core idea behind them, which and we refer to them as self-supervised, because the only thing they have is the input, so they do not have like anyone to teach them except themselves. So the idea is, let's one idea is based on masking, and it was proposed in NLP for BERT model that we actually saw yesterday. And we want to learn meaningful representations of text, like that we can later, for example, you do classification on text or some other tasks. Let's say we had some input sequence and we masked one word, like we kind of removed it from the sequence with a special token mask. Now, the goal of our BERT is to predict what word was in place of this mask token. So here it says improvisation, we replaced it with mask, and the goal of BERT to understand that we masked the word improvisation. And it works similar to how we saw it in generation, where we have a vocabulary, we have this vocabulary represents all possible classes, and we use a fully connected layer plus some softmax to define which of the words is correct here instead of this mask place. Clear? So then, because now, so the goal is basically based on the context, the model understands what was the missing word. So it's better in understanding text right now, because it's like kind of learns what sentences are meaningful, what sentences are not meaningful, how text is actually structured, etc. So then, as we discussed yesterday, we can just add this CLS token at the beginning, and it will collect all information about all the sequences we had into one token that we put our MLP on top of it, and everything is going to work. And we can either fine-tune it, this model, or use it as a feature extractor. So we can say that J and DNN are both trained together, or we can say that let's compute all these features from our DNN, and now we only train the J, the small MLP itself. Both approaches can work, and it depends on how much compute you have, what is the amount of data you have, etc. In my experience, usually one works better, but it's not always doable when you have huge neural networks. And like if this model is extremely huge, you cannot just train it fully so easily. Questions? Yeah.
So I'm not very clear about this feature extractor and its relation with this mask model. And the mask model is basically mask some words, and they don't have a model to predict this word, right? But I mean, what is a feature extractor?
So to be able to predict the masked word by its context, the model needs to understand the context pretty well. It needs to understand how text is structured. It needs to understand what is the meaning of each of the words. It needs to understand that if these words are next to each other, then probably there is some other words like before it or after it. So basically, with this self-supervised thing, the model tries to understand how the text is structured, how the text, well, like what each of the words mean, and it does it better than just doing classification without this pre-training.
Without this feature extractor, and this is still the self-supervised, right?
So after you train, you train it like this, then you can use it as a feature extractor, or you can use it as a feature extractor that is also trainable. You fine-tune it. So it's fine-tuning or using a feature extractor is not. So we trained it here. Now we want to use it for our other data sets or for some other projects.
So this is the feature extractor.
So this is the training scheme with masks. We trained with masks. Now we have something which represents our text very well. So by passing the sentence through BERT, we get new representation of our text, which is much better in terms of and much easier in terms of understanding like what text is about. And we can either use these features as is, as this is called feature extractor, or we can also want to adapt them. This is fine-tuning what it is about. And we can do the same thing for audio, for example. So the idea is similar. And the model here is called Hubert. And instead of, so we need some quantized like clusters of our audio. So here we cannot so easily mask like we did with text. Yeah, we need to first of all come up with some token-like sequence-like representation. So we do some CNN feature extractor here, and we try to mask it. But the question is, after we masked it, what we should to predict? The problem is that this CNN output here is are vectors in Rn. So they are kind of continuous, so-called continuous. What we actually wanted to have here is to have some sort of vocabulary where we knew that all possible masks are one of n big possible words. And when this z is continuous, it's very hard to say that it's one of these n possible vectors. So one idea how to handle it is to use codebooks that we saw yesterday for audio. Another is to use some spectrogram-like representation of our audio and do some machine learning method which is called k-means clustering, which basically says let's split our input into k possible representations, k possible clusters, and when we mask, we want to predict this number of cluster, like what's the cluster ID that we used. And basically we train it in the same way as we did with BERT, and we can do the same for vision, which is vision Hubert, yeah.
Here, the number of tokens for an object is fixed, or it depends on the length of audio?
So the number of clusters, you means. The number of clusters, as far as I remember, is fixed. You predefine it.
If there are like 7 like 2 tokens.
Yeah.
Same cluster, so do you define the number of tokens?
Yeah, you kind of predefine the number of tokens beforehand. You say that let's represent our audio with, let's say, 50 possible clusters. And each cluster, so it's not so well, it's not so fine-grained as it was in text, where each word or each small word is a specific index. It's a bit larger thing. just because it's more complicated to represent audio in this token-like way, and it was before these quantizers that we saw yesterday became popular. So it was kind of old paper. But yeah, so because of these clusters being quite large, it's possible that the first part of the audio sequence goes into, even though it's like noticeably different, it goes still into the same cluster because the cluster is large. Okay. You also have a question.
What's the K number? Like, what is it in hyperparameter or something?
Yeah. Feature extractor is a DNN we talked about previously. What feature extractor is how we can use our pre-trained model. So I don't know if you have an example here. Basically, because we are out of time and people already there, I'll just say that we can do the same for vision with exactly the same way. We can do the same for multiple modalities. We can either use something like late fusion that we saw yesterday or early fusion. And we can do it with another approach, which is more similar to quantized representations we saw yesterday, where we try to quantize the output of CNN itself without these clusters, which is probably better. And this can work for audio. It also improves your results in different tasks. For example, anti-spoofing or deepfake detection that we are talking about today, because when new method comes out, like new falsification method, and it comes out like every semester or so, you cannot like retrain your model continuously, especially if this neural network is not open sourced. So it's very hard for you. So in order to be able to generalize to these new falsification methods, you need to pre-train on this huge amount of data. That would and you would benefit from having huge distribution, knowledge about some huge distribution. So what you can do, you can say, let's pre-train our neural network, so our self-supervised neural network, on a huge amount of data, huge amount of audio, and convert our waveform to this self-supervised representation, to these embeddings. And then if we are saying that we are working with this feature extractor way, we would calculate this once, fix it, and forget that we had self-supervised model. We will say that now our audio, like our tensor of this audio tensor is always represented like this, and it never fixes. So it's a fixed representation. Or we can say that we are in fine-tuning case, where we say that because we are trained only on real audio, it might be better to also fine-tune our model a bit so it can work with fake audio, with falsified audio too. And we slightly adapt these calculated features together with something we have on top of them. And regarding having something on top of them, we can just have like a fully connected layer, and this works pretty well. And having this self-supervised feature extraction gives a lot of benefits. We see that without it, our metrics are pretty poor. But if we add any type of these classifiers on top of self-supervised models, our metrics improve significantly. And it doesn't happen only in audio, it happens in many other domains too. And one way to write a paper is to find a domain where nobody for some reason uses self-supervised models and use it the first, like being the first who used it. And saying, oh, we found that it performs better. And you cite 10 different papers that do exactly the same thing, but in different domains, but you still like get through review and you go to a conference, which is nice. So any questions?